All right. Hello, world. Um, so let's see if I can show you what we're looking at. Okay, so I'm going to look at 60 through 64 today. Maybe I'll do another in a few weeks. You know, when we get to 70, I'll do the next five. So we're looking at number 60. This is a complex analysis question. It asks, what's the principal value of this complex number? So principal value is a hint that you're going to use a logarithm to evaluate this thing. Generally, when you take log of a complex number, you get a magnitude and an argument. So here we'll have arg z. So usually prior to talking about logarithms, you first talk about polar coordinates and maybe arg with a capital A, refers to the principal value, meaning a value between like negative pi and pi. And then the lowercase version of arg refers to the fact it's a multi-valued function. It refers to the fact that if you were to add 2 pi to your angle, you get the same complex number back. So you can always add a multiple of 2 pi to theta in your polar coordinate when you're in polar coordinates, and it'll give you the same value back, right? So these are basically saying the same thing, except that the capital version is a single valued function. So that's your principal value, and this argument of z is the angle that you would get for theta, except that this is restricted to negative pi to pi. This one is basically just capital A plus 2 pi k, where k can be any integer at all. What else do we know about logarithms? Generally, the logarithm is this value omega. So for z, if you had e to the omega equals z, omega would be log of z. So you want that to happen again. That's part of the definition. Anyway, without further ado, let's just evaluate this one. So it's asking what's the principal value, implying that there's potentially multiple values for this thing, but we just want the one where the angle is between negative pi and pi. What I would do is I want to take a logarithm right away so I can pull this I down. So write this as e to the log of the original stuff. Let's do it this way. Does that make sense? Right. So anyway, we've got e to the log I to the I. You can pull the I down and get e to the I log I. So now we're just focusing on what is log I, and the rest of it should be pretty smooth. So just recall this. It's sort of a fundamental definition in complex variables. So pretty early on, they talk about logarithms, and when you have a log of a complex number, you've got a magnitude and you've got an angle. So that's what we're doing with this I. So you maybe want to recall that I shows up here, of course, when you've got an angle of pi over 2. At least that's the principal angle. That's the one that's restricted from negative pi to pi. So just as a little comment here, log of I is, and I'll just use this definition, it's the natural log of the magnitude of I, which is 1, so we're getting 0 there, plus I times the argument of whatever you were talking about here, whatever this argument is, z. So here we're getting 0, Here we're getting I times, and the principal argument is pi over 2. So I would think log of I is I times pi over 2, or more generally, it's really I times pi over 2 plus 2 pi k, you know what I mean? More generally, log of I is something like this. But we just want the principal value, so never mind that. We don't need multiple values in this conversation. So yeah, you got that. Multiply it by I, you'll get negative pi over 2, and we're basically done with this problem. So not as bad as it looks, but you have to be comfortable with, you know, with principal values and with using a logarithm and stuff like that. So now I'm just going to say that I log I is I times this. So we're getting negative pi over 2. And e raised to that is what our original complex number was. So I'm thinking of I to the I as e to the log of I to the I. But here's log of I to the I, at least in principal value. All right, so what do we want to say? I guess we're done now. C is e raised to negative pi over 2. And that's our answer on this one that you see in the corner here. So yeah, principal value on this is e to the negative pi over 2. There's still other value. This is a multi-valued number, but the principal value of it is e to the negative pi over 2. All right, we'll move on. And the rest of these today are a lot easier. Let me think. I usually drop these questions Mondays and Thursdays on the site, you know. So I'll have another problem like tomorrow morning. Well, actually at midnight tonight. You'll have 67 will come out. Here, let me blow this up so you can see it a little better. So yeah, next week will be 69. Today I was going through here, so 5, 6, 7, 8, 9. Yeah, so I guess next Friday I can probably do. I'll probably make another video either next Friday or a few days after that for the second half of these. But then they get pretty easy today, so. Yeah, the rest of them are not bad, right? Pre-calc, discrete, calc, and calc 2. Those ones are not as bad as this complex analysis question. They're also starting to get tough. I don't know, I'm just thinking out loud. Because as you might be aware, every 10 questions roughly corresponds to, I mean, there's 10 different subjects, and each question in a subject is another week of the material, basically. So what I mean is, this is basically a question from like week 7 of a course. You know, if you were taking a course on complex variables, you'd probably see this about a month and a half into the class. All right, so anyway, back to the story. So let's move on to pre-calc. This one's not as terrifying as the complex analysis question, of course. So this one says we have this function 2 over root 3x, and we add 5 to it. Find the inverse. Okay. You can just solve for x, or you could swap these and solve for y if you prefer to do it that way. Let's do that, I suppose. So we have x equals 2 over root 3y plus 5. Solve for y. And then you'll have a function in terms of x, and that'll be f inverse of x. Okay. anyway, this is just some sort of basic algebra. If you subtract 5 from both sides, you'll be looking at this. So you have this thing sort of isolated. I suppose you could take the reciprocal now if you want. I want to flip this upside down because I want the y on top. So you could just take 1 over this is equal to 1 over this, or you could square right now. It doesn't really matter which you do. So now that I've got it isolated, I want to both square and take the reciprocal. So I don't know, let's square first. If you square first, you'll get this squared. And you don't necessarily need to expand that. I wouldn't bother. On the right-hand side, we square, we get the top square. You know, we're doing something like this. If you had a over b squared, you get a squared over b squared. So we're getting 4 over, and then when you square the square root, it cancels and gives you 3y. So now you can take a reciprocal if you want, or you could multiply by this denominator and divide by that. Either way. I said I would take a reciprocal, so let's do that. So if I take the reciprocal, I flip this upside down, I get 1 over that stuff. And then over here, I just flip it upside down. I get 3y over 4. So let's multiply by 4 and divide by 3. And you'll be left with y is, let's see, multiply by 4, divide by 3. And we had this stuff squared. Stuff is x minus 5. And I would leave it like that. There's definitely no reason to bother expanding that. This is usually what people want to see for the inverse function of this. So this mess is also known as f inverse of x, and that's about all on this particular problem. Let's move on to 62. I'll have to update this. I don't know why it's... I'll zoom in a bit so you can read this. So, yeah, I'll edit this at some point. I didn't realize that the question got all mangled. But anyway, we're selling 1,000 raffle tickets. This is an expected value question. So it involves a little bit of probability and a little bit of like some value, some output. So like, you know, sometimes like you're rolling a die and the values that you see are the numbers, the number of pips on the die. In this case, I think the value that we see is probably some cash amount. It says there's a prize worth 300, 2 prizes worth 100. Okay, so we have 1,000 raffle tickets, implying, of course, wait, sold at 1 each. Okay, I think I see what happened now. In LaTeX, a $ is the indication of like a variable. And you can see it, yeah, it stopped being crazy when I hit the next $. Let me zoom in again. So when I hit $300, it closed the variable. It turned everything in between the sentence into math speak. Anyway, I'll fix that later. But the point is, tickets cost $1. And then there's 3 prizes. There's 1 prize worth 300. There's 2 prizes worth 100. And there's 4 prizes worth 50? Yep. So these are the potential winnings. What's the expected value of this when you purchase 1 ticket? So if there were no prizes at all, you purchasing a ticket means you lost $1. Like, so in general, most people, this is their outcome. But for one lucky person, they're going to win $300. And so their total net is $2.99 because they did spend the $1. So if you were to make like a table, if you were to say x is a random variable representing the cash that we win, and I'll just say net to really emphasize that it includes the cost of the ticket. Okay, so if x is some random number, one person out of 1,000 is going to get not quite 300, but 300 minus 1. So you could get 299, you could get 99, or you get 49. Or if you're like the vast majority of people, your value, your winnings, is just nothing. You lost $1. So x is what's called a random variable, and it has some distribution. It has some likelihoods attached to each one of these values, right? So like, I don't know if you haven't seen this before, here's a little side example. If you talked about rolling a die, you would have these outcomes. And then each outcome is equally likely in that particular case. So you put probabilities over here. I'll put P of x here, okay? So I'm going to put another column in my table called P of x that describes the likelihood, some real number between 0 and 1. And so for a die, you just put a sixth, a sixth, a sixth, right? This is called a uniform distribution. And then there's a formula when you talk about expected value. It's like, what do you expect to see on average? And there's a formula for that. It's the sum of your probability times your outcome. In other words, in this case, the simple example, it's 1/6 of seeing a 1 plus 1/6 of seeing a 2, and you just add all those up. So it's this product plus this product plus this product, all the way down. I'll quit doing this here. So that's the background information. This is what expectation means. This is or expected value. This is your expectation when you roll a die. Is 1/6 times the sum, and that works out to be 7 plus 7 plus 7. So it actually works out to be 21/6, or 7/2 is another way to put that, okay? So your expected value when you roll a die is 3.5, which maybe feels a little weird, but it's actually right in the middle. So just another comment, notice that that's not even a possible outcome. It's okay for your expected value to not be one of the outcomes of the random variable. In fact, it's pretty common. Anyway, back to our story. This is a quick and easy problem if you know the definitions. The question was, we're going to sell 1,000 raffle tickets for $1. One of them will reward you with $300. 2 of them are worth 100, and 4 of them are worth 50. So you were implicitly told here what the probability is, assuming that it's all fair game and stuff. You know, assuming the person selling the tickets didn't like hold on to the winning ticket themselves. So assuming these things are distributed randomly, of course, this one ticket has a 1 in 1,000 chance of occurring. Like when you buy a ticket, there's 1 in a 1,000 chance that you got that one ticket, right? So that's the probability here, is 1 out of 1,000. The $100 tickets, there's 2 of those, so I'm going to put a weight of 2 out of 1,000. There's 4 $50 tickets, so there's 4 out of 1,000 chance of getting that likelihood. And then the complement of the complement of having positive winnings, you know, sort of the opposite of this is what's going here. It's a huge number. It's close to 1, right? There's 4, 6, 7 ways that you win, which means there's 1,000 minus 7 ways that you lose. Is what, that 993 maybe? So there's 993 out of 1,000 chances that you lose. So this is a typical way to do the problem, and now we just do our formula like I said before. Now if you want the expected value of x, I'm going to show you a little trick here in a second after I write this out. But we're just doing this straightforward. The rest of the problem is to say, all right, this likelihood times that value plus this likelihood times that value, just all the way down the line. So there's a 1 in 1,000 chance of you winning 299, like of you seeing this value from your random variable. There's a 2 in 1,000 chance of you getting this as your your value. There's a 4 in 1,000 chance of you getting this as your value. And finally, there's the complement, because this sum of this column has to add up to 1. If it doesn't, we made a mistake in this. This is called a probability distribution table. But if this doesn't add up to 1, we're missing some of the outcomes. Okay, so that's how I knew that this adds up to 1,000. I knew that 1 plus 2 plus 4 plus whatever this is had better be 1,000, or we're missing some outcome. But anyway, that weight times this value, or this outcome of your random variable. So the majority of the time when you buy a ticket, you just lose the dollar. But some tiny fraction of the time, you get one of these outcomes, which I guess is good. So you can grab a calculator, crunch that number, you get some dollar amount, and that's our answer. But I'm feeling kind of lazy. I don't think I want to do that right now, because I just don't want to deal with this number. And there's nothing wrong with doing this, right? It's like 299 plus 2 of these, so it's like 299 plus, what's 2 of this? 180. You can tell, why am I having such a hard time with this? 2 of this would be 200 minus 2, right? So 198. Okay, so 198. And then 4 of these is almost 200, but it's short by 4, right? So 196. And then we have to subtract this one. So you're subtracting 933. So it's whatever that works out to be is what we put there. But let me show you a trick. Instead of doing the net from the get-go, you could just realize, oh, we're going to subtract $1 from everything when we're done. Okay, so instead of saying net winnings, you could just say like gross winnings, or like whatever you win on the ticket. So for the majority of people, they win 0, and your outcome is 0. So another way to do this setup, instead of having x be net winnings, I could have let x be just like gross winnings, just the cash that you get from, as resulting from your ticket. In which case, you could get 300, you could get 100, you could get 50, but most of us get 0. And then these probabilities are, of course, the same. So this is still 1 out of 1,000, 2 out of 1,000, 4 out of 1,000, and then this is 993 out of 1,000. But it almost doesn't matter that it's 993 because it's going to be multiplied by 0. So I'm going to do something different. I shouldn't have used the same variable name. Sorry about that. Let me call this x prime or something, okay? X prime. It's a different, this is not net, this is just gross winnings. So my expected value of the gross winnings variable is, again, same story. 1 of 1,000 times this, plus 2 out of 1,000 times 100, plus 4 out of 1,000 times 50. But now, this stupid number I don't have to deal with. It's going to be times 0. So you can see why I did this, because I don't like multiplying. So that's not really there. It's a 0 times that term, okay? But when I'm done, don't forget that it did cost you $1 to play the game. So this isn't actually the correct answer. When I'm done, I have to subtract 1 from it, and that'll give us the same answer. So anyway, this one now is 300 over 1,000 plus 200 over 1,000 plus 200 over 1,000 plus 0 over 1,000. Looks like it equals 700. 700 out of 1,000. 700 out of 1,000. But do not write that down, because that's not actually your final answer. What's this, 7/10? So it's like 0.7. So if the tickets were free, then yeah, that would be your expected value. But because they cost $1, I now have to subtract 1 from this number. So our actual expected value, this apparently, if we had done it out, the expected value for your winnings, your actual net winnings, is 0.7 minus 1, which is like negative 0.3. So you're going to lose, on average, on average, you would lose 30 cents by playing this game, which I realize doesn't make any sense. You'll lose $1, But this can give you, I mean, first of all, not only is this true, it's sort of like the median winnings, if that means anything. I should say it's the mean. It's literally the mean winnings. Um, but it tells you, because this is negative, it tells you this is a losing proposition. You know, if this had been positive, then absolutely you should play this game. That means that you're on average you're going to win. It doesn't mean you're going to win that amount, but it means you'll win. It's worth playing. So the expected value is like a very practical thing. It gives you a way to tell whether something's worth playing or not. And of course, like if you're at a casino, every one of those games has a negative expectation, or they could not possibly run that game. They'd be losing money. And I think I can't remember off the top of my head. I would guess that like roulette has maybe the closest to zero. Like, of course, every game in the casino has a negative expectation, but I would think maybe roulette at least has some control. And the trick with roulette is that those two, the zero and the double zero, throw it off so that it's no longer an equal game. The fact that those exist makes the game slightly negative expectation for you. If they weren't there, it would actually pretty much just be an even game. So that's why my instinct is that roulette is probably the closest to a fair game at a casino. But blackjack is also not terrible if you like play correctly. Play properly. But no, don't quote me on that. That doesn't mean you should go out and play blackjack. Hey Rex. So let me look at the next problem for us. So a little more dry, um, perhaps a little less interesting for us common folks, is a calculus question that says, find dy dx, find the derivative, I suppose, of this curve. Oops, sorry. X to the 4 plus y to the 4 equals 10. So I don't know what this looks like off the top of my head, although I do know if these were squares, that would be a circle. So that's good instinct. It's probably something like a circle that's been kind of bent out of shape a little bit at the edges or at the corners. I'm just winging it. You could also rephrase this. It is x squared squared plus y squared squared, if you really wanted to think about what this looks like. We don't need to do that, though. So find the derivative using implicit differentiation. Generally, if you're a calc student, if you are a calc student, as soon as you see the word implicit, you're off and running. This is a whole method that you use. Before you're taught implicit differentiation, you're taught the chain rule, meaning well, for example, if I had something simple like 3x plus 1 squared and I want its derivative, we have this power rule thing, right? So first of all is the power rule. If you had u squared, you do 2u to the 1, for example. I'm just giving a little bit of background for the questioning so we don't jump right into it. So we have power rule. So when you see this, your instinct is to be like, oh, power rule. I see something to the 2. So we put 2 to the 1. And then the chain rule says what you should do is evaluate this answer that you got, evaluate it at the inside stuff, and then multiply by the derivative of the inside stuff. In other words, if you have, like if you want d dx of u squared, where u is a function of x, then what we get is you take the usual derivative, 2u, but then you multiply by the derivative of, I made that super clear, didn't I? You get the usual derivative times the derivative of u. So I describe this as like the derivative of the inside is popping out. We're going to multiply by the derivative of the inside. There's that mantra in my head every time I mean, you do that all the time, actually. But anyway, especially when you've got a function that's not just 1x. So back to our question. I basically want to take the derivative operator against the left and the right-hand side, and I'll see what happens. On the right-hand side, we have a constant, so of course, that's a 0. But on the left, we have, okay, it's a sum, so we can split it into two pieces. And then it looks like there's two powers. Now, d dx of x to the stuff, that's easy. But what's weird, the reason I brought up the chain rule, is that y is, it's thought of as a function of x. And part of the reason you know that is because it says dy dx right there. So just writing dy dx immediately tells you they're considering y to depend on x. Okay? But they want us to find dy dx, which means x is the independent variable. So this part, x to the 4, that's a little more normal. You don't really have to think about the chain rule for that particular part. But when you see another part, if it involves y, you gotta think of it as like, oh, that's a whole function. I don't even know what that is. There's some big expression there, y of x, you know? So it could be like this. Anyway, that's probably good enough for background motivation. So how do we do this? This one's a power rule. You just write 4x cubed. But this one, you want to think of it like the way I was thinking of this. Like, I don't know what that y expression is. It's just something that we're calling y. So it could be this. It could be even worse, right? So I just want to remember, when I take its derivative, I'll do the usual thing, the power rule. Then I evaluate at the inside, and I multiply by the derivative of the inside. Or you could put y prime there, if you like that notation better. And we're almost done. We're basically done with the hard part. Now you just want to solve. Now you're doing some algebra. Solve for y prime. And that's it. This is an easy example, I suppose, but you should not be surprised if your answer, when you're done, depends on both x and y, and it's a big fraction. You'll see what I mean in a second. So we want to solve for this part. I guess that means you should isolate this part. I'm just doing some algebra here. So subtract 4x cubed. You'll get 4y cubed y prime. I'm going to subtract 4x cubed. And then I'm going to divide by this extra stuff, because I just want to get y prime on its own. I want to solve for that. So we're going to divide by 4. And we're going to divide by y cubed. 4y cubed. And yes, the 4's cancel. Go ahead and do that. But I wouldn't do much else with this. If you like, you can write it like this, I suppose. You don't have to. This is our final answer. That's not wrong, even though it has a y in it. This formula is dy dx. This is very common. This is extremely common in these implicit differentiation problems, for your final answer to be a big rational function that depends on both x and y. That's standard stuff. And if you think about just a quick example, it's not this example, but if we did have a circle, x squared plus y squared equals 1, say, if you did have a circle and you asked, what's the derivative right here on the circle? Or what's the derivative right here on the circle? What's the derivative here? If you wanted to find dy dx of this expression, notice that it depends on both x and y. You know, here the slope is the derivative there, but up top the slope is 0. So it looks like if x is 0, we're getting a slope of 0. I'm not going to do that example out because we just did a more interesting one, but it looks extremely like this. It looks like negative x over y. So yeah, it is not surprising at all to me that, for instance, the slope of this kind of shape depends on both x and on y. Um, it should depend on both x and y. All right, ladies and germs, let's move on to our next problem. All right, and this will be my last one for today. I decided to split these up. Before I was doing 10 problems at a time, but they are getting a little harder, so that was taking like an hour. So this is going to be a little shorter today. So today we just did 5 problems, 60 through 64. So yeah, Calc 2. Is this convergent or divergent? To be honest, these guys are not as bad as they look. Well, they can get very bad, but usually when you're in Calc 2, when you're doing the series stuff, you have a handful of things, like a handful of tricks in your bag. And then you have a few things that you know early on. Like you learn early on that this is a divergent series. The harmonic series is divergent. And for me, the easiest way to see that is that I compare it to the function 1 over x, which if I started at, say, 1 and I integrated up to like t, this is log of t. In fact, the way I was taught, this actually is the definition of log, or it's one way to define a logarithm. The natural logarithm is as the integral of 1 over x. Anyway, I bring that up because this is called an integral comparison. Like, of course, if you have, say, the function 1 over x, right? You can inscribe this series inside of it, of course. You just evaluate at the integers, you'll get a sequence back. So if we were to evaluate, say, at 1, you get this little box, and it's under the, well, the way I've drawn it, it's under the curve. Okay? But we could also go the other way. I could do the same curve, 1 over x, right? There's my 1 over x curve. And then I could say, I'm going to take, what is this, a right-hand sum? So now I'm going to take a left-hand sum. I'm going to use 1 to give me the left-hand height of a square, of a rectangle, excuse me. And then when I evaluate at 2, it'll give me the left-hand height of a rectangle. And when I evaluate at 3, it'll give me 1/3. And at 4, it'll give me 1/4. Okay, so you can see that depending on how you set it up, you can definitely compare this sum to this area, the area under the curve from 1 to infinity, which we know is infinite because log of infinity is infinite. So it doesn't have a convergent limit. Like this improper integral is not finite. So I know that this area under the curve is not finite. And I just basically expressed the harmonic series as, you know, in comparison with this improper integral, which I know is infinite. So we just proved that the harmonic series is divergent. This picture proves it. You know what I'm saying? And what else do we know? Another thing that we know, well, same logic basically. Functions like this will be finite. I'm not going to bother to prove it, but this will be finite if p is bigger than 1, which tells you that, by the same kind of logic, that the sum of something like 1 over n to the p for a fixed p, where p is bigger than 1, will be finite, weirdly enough. So this is called a p-series. Another little trick that Calc 2 students keep in their pocket. Hey, thanks, Rex. So that's what I wanted to make sure you remember on this particular problem as background information. I haven't thought about it too much, but one thing I'm noticing is that it's divided by a function of n. It's basically a harmonic, but it's a little smaller. It's a little smaller than a harmonic, which instinctively I'm like, oh, it's kind of like one of these where p is bigger than 1. It feels like this should converge. I haven't proven anything yet, and I'm not going to actually prove it that way. I'm not going to just say like, oh, I guess the power is bigger than 1. That's a kind of a hand wavy argument, right? But that's what it feels like, right? And you could maybe get away doing some sort of what's it called? Well, you could maybe do a limit comparison test on this with something that you're familiar with that you already do know converges. But what I'm going to do is pretty much just what I did here. I'm going to say, like, is there an integral? Like, what if I looked at this integral? Would this be convergent? If I just if I got the area under this curve, and I don't really know what this curve looks like, I'm just going to pretend it looks like this. But I don't know if it's finite or not. Could we solve this maybe? Like going from 1, yeah, from 1 to infinity? Is this improper integral, finite? Is this actually an integrable function? My instinct says yes. So I'm going to try this, and if it doesn't work, then I'm in trouble. Cancel. Maybe. So I was thinking it might be this, and then because then I'm looking at something like 1 over u squared. We'll fix the details on that, but this is something that I know is finite, right? We just sort of just talked about that, the p-series stuff. So I think our integral looks like this, but I'll see. So if we do a u substitution on this integral here, if I let log be u, I guess it changes our numbers a bit. This lower bound becomes log of 1, 0. Huh. Uh-oh. Do I have problems? I guess we don't have to start at 1. Does this start at 1? It could start at 1 if you want, but there's nothing there, right? Because log of... can't start at 1. Yeah, that's a typo. Okay, look at that. You see this starts at 1. Log of 1. This is what I get for making up problems, right? Yeah, that can't start at 1. Oops. It doesn't make any sense at 1, but let's assume it started at 2 instead. Then this is 2, then this is log of 2, okay? That's a little better. That makes a little more sense to me. Looks like I have another problem I got to update. But yeah, I'm trying to do a u substitution. This part, 1 over x dx, is about to be replaced with du. And we've got, of course, 1 over u squared. So integral of u to the negative 2. If you just like add 1 to this. So I'm doing the power rule, right? The integration form of the power rule. If I add 1 to this and I divide by the new power, and then we can evaluate from whatever to whatever. So here we get log 2 to infinity. In other words, negative 1 over u is this formula, and we evaluate at the top and at the bottom. So I'm just going to, I know this is a bit of an abusive notation, but this is the way I would normally do it, is negative 1 over infinity, minus this function, and then you just evaluate the bottom. So this function evaluate the top minus this function evaluate the bottom. Of course, the negative of this negative adds, you get 1 over log 2. And this, I wrote it, I know that's kind of nasty, but in the limit, you would get 0. I mean, a more appropriate way to write this, if you're being a stickler, is of course to say, negative 1 over t, it's like the limit as t goes to infinity, plus 1 over log 2. Anyway, the point is, this is our answer. Why do I care about that? This means this is finite. This is finite, which means our series is also finite. So I usually call that an integral comparison. Maybe that's, I'm not sure if that's the name. But by an integral comparison test, this guy is convergent. Of course, I don't know what it converges to, but I suppose you could argue that it's less than this, right? You could bound it in this manner using right-hand sums. And you could say, all right, my series is less than the area under this curve. And so this is a maximum for what this sums up to. But in any case, it is convergent by integral comparison, or yeah, by integral comparison. That's what I would say if I had to say it in one sentence. And it turns out you can do a U substitution on that puppy. Assuming the bounds are set up correctly, nyuk nyuk. All right, ladies and gents, I'm going to disappear for a bit. Thank you for popping in and checking out David Does Math Challenges. And if you enjoy this stuff, you should check out my website, .org, excuse me. So as you can see, I've got like 10 different topics here. Some of them are pretty straightforward. Even if you haven't had calculus, you could probably handle the pre-calc and discrete stuff. Discrete stuff gets interesting. There's some probability in there. Counting. And generally, I go through and I put my submissions in, my answers. So you have a way to check your work. But I will disappear. And I'll probably do, maybe next Friday I'll do another set of 5. But it might be a few more days, something like that. Could be like 2 weeks from now. It's roughly once a month we get 10 whole, well, that's not true. It's 8 problems each month. I've slowed it down to do it twice a week. So we get 2 new questions a week. And so for instance, Monday's question was this differential equation system. But then on Thursday, actually tonight at midnight, there'll be a linear algebra question. Number 58 will be up there. Or 68? Huh. Yes. 68. Excuse me. 67 is what I'm saying. Are we on 66 now? Yeah, okay, good. So yeah, number 67 will be posted tonight at midnight. It'll be a linear algebra question. And it's following this. The previous question was on determinants. Prior to that was a Lontief input-output. So you can kind of roughly guesstimate. It goes roughly once a week. Like this was week 1, week 2, week 3, 4, 5, 6. So the next question is something that you would probably see roughly in week 7 of a linear algebra course, is what's going to be on tonight. But in a couple weeks, I'll post the next set. So I'll do this multivariable question about the gradient. And I'll do this differential equations question, which is not nearly as bad as it looks. And yeah, anyway, I'll wait till I have 5 more problems to do. And I also post this video on my YouTube. You could probably track it down here or just look in the notes, but it's under, there it is, David Ferrone Math. Oops. So it's also on my YouTube if you want to check that out. Anyway, have yourselves a fantastic day, and I will see you soon. Later, Gators.